Now the session 4, it gives me immense pleasure to introduce our esteemed speaker for this session, Dr. Mishra. Dr. Mishra is an accomplished academic and researcher with over 20 years of experience. He had held prominent roles such as head of the department, president of IIC, ESL core committee member, and many more. He is contributing significantly to academic planning and institutional innovation. He has been awarded in Erasmus Mundus Research Fellowship at the Netherlands, and the MHRD Fellowship during his PhD at NIT Roorkee. Dr. Mishra's expertise spans pattern recognition, computer vision, artificial intelligence, and feature extraction, with more than 50 papers to his credit in various journals, conferences, and book chapters. He has secured multiple research grants, including INR 30 lakhs from SERB and Government of India, and has guided 5 ongoing PhD candidates. He has also guided 1 international candidate, and he has also delivered international technical talk for the University of Binghamton. Dr. Mishra accolades including winning multiple hackathons and ideathons such as Smart India Hackathon 22-23, and he holds 12 patents. His editorial roles including serving on boards like PLOS1 Frontiers in Artificial Intelligence. Presently, Dr. Mishra is working as Associate Professor at Manipal Institute of Technology, MAHE Bangalore campus. Dear all, please join me in welcoming Dr. Mishra, sir. Welcome you, sir. Sir, please click on yes.
Yes, thank you, Sweta ma'am. Thank you. I'd like to thank Dr. Suresh sir and the authority of Malla Reddy College of Engineering and Government of India for giving me this opportunity to talk to be with our professors, beloved professors and friends and seniors as well. Yeah, let me start the presentation. I'm sharing it. Am I audible, ma'am?
Yes, sir. Yes, sir.
You are audible.
Yes, sir. Yes. Yes, hopefully this slide is visible.
Yes, sir. Visible.
Yes, sir.
Yes, yes. So the topic is UNET, Convolutional Networks for Biomedical MS Segmentation. And there is a proof of IBET revolutionizing the biomedical image processing. We'll go like this. Medical image analysis, a little bit introduction to that. Medical image segmentation, followed by the challenges presently being faced by researchers and experts. Then it will be followed by applications, importance, goal. Then we'll start with the specific topic meant for today, that is the UNET. It's not that big. UNET name might be is little bit new to us, but it's not that big topic. And we'll do hands-on because this is Atal FDP and little bit workshop concept involved. So a little bit hands-on also will be doing with that. And yeah, there is some, okay. Yeah. So before we talk about this medical image analysis, generally I start my talk with one verse from Gita. Like the first verse, what it says is Dharma Khetre Kuru Khetre Samabeta Jujusava Mamaka Panduschaiva King Karoti Sanjaya. This is the question being asked by King Dhritarashtra to his assistant Sanjaya. Sanjaya was Dhritarashtra is blind person. Sanjaya was capable of seeing, sensing, visualizing anything from any place of the universe. So he is always throughout the time depicting the incidents, events, everything happenings of the Mahabharata Yuddha. So from this, we can say the computer vision Indian scenario, we can have an inference. Like there might be combination of, we don't know that Sanjaya is a real human or is a framework which is having some organs, artificial organs connected through IoT with the workplace, warfield, sensors, cameras, high satellite imaging, and everything being connected wirelessly with high-speed accuracy, and is capable of delivering the outputs through several outcomes like speaker. So in that context, computer vision, one of the possible domain is medical image analysis, and again the subdomain we can consider the medical image segmentation. Medical image segmentation, image processing, and computer vision mostly concerned with this topic. So what we see is visualization of human body through medical through digital imaging. Medical image help visualize tissues, organs, different body parts, and not just to visualize. The visualization is meant for some semantic outcome such as diagnostic and monitoring of definitely ailments, some disturbances in human body and all. Key applications includes disease detection, some prediction and detection of ailments, treatment monitoring, how well a drug or an invasive surgery is affecting the organ body part, and also to do surgical planning in near future. The key steps when talking about the technical aspects, right hand side, the key steps in medical image analysis, these are the key steps just like image processing phases: segmentation, feature extraction, classification, image matching or registration, anatomical measurement, anatomical assessment, physiological parameter extraction. So this first point, that is segmentation, that means dividing the image into meaningful regions. This is the general layman definition we can say. In this medical image segmentation, what is happening, why this is being too much specific is in normal cases, first point you can see is that is not, those are not fatal in nature, those are not associated with that much life risk. When it comes to medical image analysis, any XYZ algorithm might not work that well, or it may give a false alarm which may lead to a severe outcome, may lead to death of a person as well. That's why the segmentation part through computer vision and image processing and latest deep learning or maybe advanced AI algorithms is too much necessary. And in context, we'll be seeing UNET. Remaining all the phases such as feature extraction, classification, remaining analytical phases, those are all not of our interest for today's session, maybe some other day. Why medical image analysis? What are the benefits? What should be the goal or objective? So these are the key points I have noted down. Medical image analysis, we generally do it for detection of complex diseases. Complex diseases may be like lung and breast cancer, brain tumors, or presently there are the regenerative medicine, a very emerging domain coming out in the market. People are rushing for admissions to this course as well, and many research problems have been, a volume of research problems have been deployed in the market, where all of us can also choose and work together in that domain as well. This is also for clinical support, point number 2, which will help us in assisting doctors, the algorithm or frameworks that if we can come out with an accurate algorithm or framework related to medical image analysis, that then we can help a doctor, a physician to diagnose and treat and also do treatment planning. Along with this, supportive expert systems are also needed. So blend of computer vision and AI. Database management, medical insurance, all of us mostly we are having medical insurance. However, when patient is undergoing treatment, how much drug is being administered, what kind of surgery and operations have been performed on the patient, whether there is a fraud happening, drug is being administered correctly or not. On that, there was a very big debate when last week in our premise with Honorable VC Jen2K as well. So that's what database management is also an inevitable part in this. Computer-assisted diagnostics and therapy, independent engineering discipline. It has become a specialized domain now, and separate from direct clinical practice. It is emerging. It has already emerged as a research topic. So these are all the importance, goals, and all. Medical image segmentation. Coming to the specific topic, there are 2 points I have noted. To highlight key areas for diagnosis, point number 1, and improve visualization and analysis of anatomical structures. These 2 are the key areas where medical image segmentation is highly desirable. Because once again, let me say, when we consider a video or a digital image of a general scene, and when we visualize a human body part image, it may be CT scan, it may be MRI, or it can be an X-ray image. So what difference lies is human tissue wise, cell wise, there may exist difference. There may exist difference, the linearity of edges and the density of thickness of edges, blobs like structures, those are quite fine-tuned. But when we talk about a normal scene image or video, there that much accuracy is not needed. Someone can skip some pixel level of edge correction, edge visualization, thickness visualization kind of thing. That's why it becomes important when important, and also this high risk factor differentiate between medical image segmentation to other domain image segmentation. In healthcare, the importance, there are 3 points I have noted down. Enabling precise detection of disease like cancer, fatal disease like cancer, assist in monitoring progression of medical conditions, aids in treatment planning and surgical interventions. 4 different approaches broadly can be followed for this segmentation purpose, medical image segmentation purpose. Thresholding, region growing, edge detection, and active contours or snacks approach. So thresholding segments image based on pixel intensity values. Pixel wise, the intensity to be considered, and in correlation with the threshold value, this segmentation is achieved. For establishing that correlation and to segregate specific object from the health image, organ image, different algorithms have been proposed. Similarly, another approach might be region growing. So it's like expanding regions from certain seed point and stopping when it encounters a boundary. This way also we can do it. Through edge detection, there are novel benchmark algorithms already available. People are also researchers are also contributing to this edge detection portfolio. And finally, active contour, following a particular curve until the same point is reached or no repetition is happening. So these are the traditional segmentation approaches. What challenges being faced? Standard challenges, 4 points. Variability in image quality, of course, quality matters. Complex anatomical structures, ambiguity in borders, and computational complexity. Now, when we talk about the first point, first challenge, variability in image quality. When we see an X-ray image, we can say that it's not a super HD quality of image. We cannot say it is a HD or super resolution image. Still, their challenges are existing how to do the segmentation task, how to achieve proper segmented objects out of the X-ray image, because the resolution is too less in case of such images. Some medical images might be distorted, and some ultrasound images, their fine-tuned pixel level, that much depth of clarity we might not get. However, we should train our computer through our algorithms so that it should be able to do all those tasks without any or with less errors. Ambiguity in borders and computational complexity. The last point is a common challenge in not only biomedical image segmentation, however, every research domain, this is a common point, computational complexity, both time and space as well. So continuing the challenges and being too much specific, annotated training datasets are small and limited. When we refer to medical databases, now also online, when we are exploring, we are referring to uh, high quality articles also, we may not observe that much bulk of medical image data readily available to accomplish our research work. Next is it requires pixel level accuracy. Next is traditional sliding window approaches, uh, like these sliding window approaches, those have become traditional, and when there are a lot of intra variation in an image between objects, then it is too much difficult to do the segmentation. There is a image taken from this source. Applications and recent advancements. When left hand side, we have noted down the applications such as tumor detection, organ classification, identification, monitoring disease progression, surgical planning. And when we talk about the advancements, already I mentioned deep learning, most common nowadays CNN, and hybrid methods, combining traditional method with some little bit of AI AI algorithms to uh, somehow improve the accuracy. Presently is in trend, and these are the advancements so far. Now coming to the UNET. UNET was developed in the year 2015 by Olaf, Philip, and Thomas. This was first presented in a conference, MICCAI 2015, and this was specifically originally designed for biomedical image segmentation. However, this also being presently used for the purpose of image segmentation in satellite imaging and identifying streets and roads and colonies and state borders, village borders, urban, rural, everything from the satellite image. Agricultural data analytics also there. UNET is being used popularly nowadays. It has certain key characteristics, such as it does end-to-end training with very limited number of images. So just before we were talking about the data limitation in medical domain. So one of the challenge, it is well overcoming. Second point, second characteristic, it says that it handles pixel-wise segmentation efficiently. So it is not leaving any stone unturned. Every pixel is being analyzed. Every pixel of the medical image is in the radar of UNET. So in that context, it is reducing the margin of errors. Very simple architecture. We have encoder we have decoder, and we have skip connections, and there is a bottleneck also that we will see. The UNET architecture, 3 components: encoder, decoder, and skip connections. Along with that, we have another concept called as bottleneck. Bottleneck is acting just like a bridge. I'll tell about that. So the encoder, or the very specific technical term, is contracting path. No doubt, UNET architecture is a specific CNN architecture. CNN, we know it is convolutional neural network. Specially designed CNN is nothing but our UNET. Google also will not find what this U stands for. This U name is being assigned for a very specific purpose. That will easily see how the name is given like UNET. Shortly we'll see. So there is a contracting path or encoder. It captures the context using convolutional and pooling layers, similar to the CNN, and it reduces the image dimensions step by step. Okay, fine. Same happens in case of CNN as well. Now, talking about the decoder, is known as expanding path. One is contracting, it is reducing the dimension of the image. That happens in CNN. However, again, expanding the dimension means from image or 2D or 3D converting to a 1D. Again, from that 1D mapping back to again and same image or 2D or 3D. That happens in this case expanding path, or called as decoder. Reconstructs spatial resolution through upsampling and combines contextual and localization features. That's why the informative features, they are unchanged. Informative features are unchanged, which got missed when we are using a CNN at the end. When we use CNN at the end, we are missing the total image information, the key characteristics of an image, which is retained in UNET. That is one of the major difference between UNET and CNN, or you can say it is one of the advantage of UNET over CNN. That's why it is a special type of CNN, we can say. The third component, skip connections. So the skip connections, what it does, it merges high resolution encoder features, means the contracted features, with the decoded feature or the expanded path. And that's how it is responsible in preserving the spatial or pixel level information. We can see a visual representation of a sample of a UNET architecture. There is an overview. Here the same we can see. However, the entire architecture, when we visualize, the shape looks like a U, the English alphabet U, and that's why the name being kept as UNET. Here, when we talk about the contracting path, left hand side we have the contracting path, right hand side we can see we have the expansive path or the decoder part. Left hand side is the, we can see the contraction part, contracting path or the encoding path. Now at the bottom we can see there is another component called as the bottleneck, the bottleneck block. It acts like a bridge between encoder and decoder. That's why the name is also given as bottleneck. So these are nothing but these input sizes. Suppose here input image, here it is having size 572 cross 572, then some standardization happening to the size of the image, then it is getting downsampled to another dimension 128 cross 128, and 284 by 128, and again getting downsampled again through bottleneck. The original size, not exactly original, to a standard size, it is again regaining along with the without losing the pixel information. So there are the convolution happening, the pooling happening using the same concept of CNN. I hope all of us we are well aware with the CNN architectures and the kind of prerequisite we can say CNN architecture and the working principle. So when talking about one by one all the components, the contracting path, here the input image, first it undergoes two unpaired convolution, 3x3 masking is done with the input image, and here we can see to the right hand side the thickened blue line, which is marked by this arrow symbol. So it is happening in a sequence, and every layer it is followed by a ReLU, followed by rectifier linear unit, a ReLU of ReLU, and along with that, why ReLU is being used? Because ReLU is very much widely used because of its peculiar characteristic, that is, it get rid of the negative values. So very much smoothing kind of thing it can bring out to the data. That's why. Okay, now followed by 2x2 max pooling operation. The pooling operation can be user specified, it can be other type of pooling also. Now the stride 2, and for downsampling in the right hand side, here right hand side we have a downsampling representation. The depth of the image is increased by doubling the number of feature channels. So it is 512. The size is taken to be 512 at the end bottom right hand side bottom. We can see the final outcome. From 128 it left with 128 and it becomes again regained to its bigger version 512 cross 64. There is the bottleneck. So just its task is to connect the contracting and the expansive path, encoder and decoder parts. It performs some unpaired convolution. So without losing or gaining any size, it does the unpaired convolution with double the size of the output image, intermediate output image of size 512. That is 1024 filters, and that's why it prepares it for the expansive path. There are only convolutions. How many? 2 convolutions involved, and there is no pooling activity performed for this bottleneck component. Now coming to the decoder, the expansive path. Every step in expansive path, it consisting of upsampling of the feature map. First, upsampling of the feature map that is received from this bottleneck, and up convolution 2x2, filter size 2x2, up convolution. Transpose of the up convolution is considered in this case, and it is concatenated with the feature map. It is concatenated with the upsampled feature map, means they are just the data is just added, the matrix, both the matrices are added, and the skip connection that we were talking at the beginning, it provides features from earlier layers. Now what is happening, because you are now concatenating, so the skip connections, what features might have been missed at pixel levels, they are now again regained because of this mapping characteristics, mapping task. This is the output segmentation layer. At the end, at the output, very output level, we got 1x1 convolution. 1x1 convolution is used to get the class level, which is in the form of vector only, array only. So we can say, if we'll summarize the key concept in a UNET, what is happening? I'm just reading out. The expansive path of the network has a large number of feature channels. Encoder has a large number of decoder has a large number of feature channels, which is allowing the network to propagate context information to higher resolution layers. So pixel information not lost. Because of this, the expansive path is almost symmetric to the original initial contracting path. Initial, just after the input image what it got, it is similar to that. So this is how it is giving us a U-shaped architecture. And the name, that's why it's called UNET. The network doesn't have any fully connected layers. If we remember CNN, in CNN we do have fully connected layers, most often, unless it is customized. The network doesn't have any fully connected layers and only uses the valid part of each convolution. So the segmentation map only contains pixels for which the full context is available in input image. Then only it will be able to do the segmentation, right? The pixels in the border regions of the images, input images, are now classified by extrapolating the missing context through mirroring the input image. So the final, when it is being mirrored with the input image, it can tell us the informative pixel part where we can focus, the system can focus and identify the segmented objects. So just a difference between CNN and UNET. There are certain points like talking about the definition. CNN, general deep learning architecture for feature extraction and classification tasks. When we talk about UNET, definition wise, it is a specialized CNN and dedicatedly used for image segmentation. It has got encoder and decoder structure. Talking about the architecture, in CNN we have convolution, we have pooling, and we have fully connected layers. There is no concept of upsampling. Of course, there is the concept of downsampling. The image size goes on decreasing and decreasing when we propagate to subsequent layers in CNN. When you talk about UNET, no doubt downsampling happens, but upsampling is also happening. Talking about the purpose, for image classification, CNN is preferred. For object detection, feature extraction, and image classification, CNN is preferred. However, UNET is preferred, especially for semantic segmentation tasks. Semantic segmentation means the inhibit informative meaning is not lost. So this is for contextual classification, CNN, but this one is for semantic segmentation. And semantic segmentation is helpful where? In medical image segmentation. Encoder and decoder, already we have talked about this. Now, this was all about a bit of theory on UNET, on medical image analytics, and on segmentation. Now I'll be trying to show through Google Colabs, I'll be trying to show how image segmentation we can achieve. Let me open my Google Colab. Yeah, one more I have. This one, okay, my two here. Hopefully my screen is visible. I have already noted down. These materials will be shared I'll be sharing with Suresh sir. He'll be sharing with respected professors. So yeah, this is one of the basic approach for the encoder. Let me take this code to Google Colab. This is a Python code. So let us run this. What is happening here? All explanations. This is the encoder blocks. We have first the 3x3 filter convolution with a 3x3 filter, followed by ReLU, rectified linear unit, that activation function. And we are doing this with the help of Keras. That first we'll do this with the help of Keras, and the code 2 that I'll show here, this code 2 will be doing with the help of TensorFlow. So let us see that. First convolution, then ReLU, then again convolution and ReLU, because 2 times when we were reading the slides we saw 2 times it is happening. And then here max pooling, same to same that we saw in the slides. Let us run this. Take some time. Yeah, so it's done. Now we'll go for the decoder part, the decoder block. We're all doing it through Keras. Here the upsampling activity with a 2x2 filter, and again convolution here through 2D convolution feature we are using it. We are doing padding as well because we are not going to lose the size of the image. We are using ReLU, again convolution with 3x3, and one more time ReLU. Let us run this. Okay. Now let us implement this. The specific library we are importing the packages NumPy. Here one cat image, suppose we are going to test one cat image. This is just a basic approach using Keras. But before that, let us upload one image as well. Cat is not there. Okay. Yeah, cat is there. Yeah, now we have uploaded the cat image. Okay. Sometimes, not sometimes, much of the time it's giving us error. This is not the logical or syntax error, rather the session errors. Let us see, we are using a T4 GPU. Just CPU also sufficient, however, much of the times it produces such error. Okay, still error is there. It should not appear. Just try again. Still not happening. I'll be sharing the output for this, or let me check if some output I have stored. We'll try with tumor image. Yeah, that is also not defined. True. That's why it is giving error. However, this is the basic approach. So yeah, that's the error. I got it. We need to write that additional code. Meanwhile, yeah, that additional code we need to write. Meanwhile, let us have a pure UNET implementation through this second set of code. First of all, a little explanation for each step that will be running over there. I've already done it here. So the TensorFlow TFDS nightly version we are taking because the version name itself is nightly. Every night they keep it updated. Let us run this. Because of this backup I have taken, most of the time because this is a free subscription I'm using for Google Colab, much often it gives error and sometimes it doesn't work. That's why I have a backup, no problem about that. Okay, so little more time. It is taking a little more time. Yeah. Now it has successfully installed the TensorFlow and TensorFlow TFDS TensorFlow data set nightly version 4.9, and now we are importing TensorFlow HDF. Okay, fine, done. From TensorFlow examples, peak to peak, and all these necessary steps will have to run. Okay, done. Now talking about the data set, this is one of the standard data set. Much of the time people they consider the Oxford triple IT PET data set, so many PET images, and it is little smaller in size, so downloading is not a big task in this context. But I need to inform all of us that in place of version 3, now we have to use version 4. The PET dataset 4.0.0 will have to mention. If we'll take 3 star dot star, then they have, I think, removed that and they have revised, updated their dataset to 4.0.0. We may get error if we'll use version 3. Let us run this. Now it is downloading and preparing the dataset. It will take a bit of time. Suddenly the internet speed also, I don't know what. Yeah, still doing it. Done. dataset Oxford Triple IT PET downloaded and prepared to the root successfully. Now we have the dataset ready with us. Now first some pre-processing need to be done. So first pre-processing like a simple augmentation of flipping of image and normalizing the images we need to carry on. So for that 4-liner code we need to run here. It is done. Now next task is to load the training dataset and test dataset. For the purpose of training, the first function let us execute. The second one, this one is for the test dataset. The size here we are considering 128 cross 128. Okay. Now we are setting the batch size and the buffer size. So each batch with 1000 samples, and there are 64 the batch size 64 we are setting over there. We'll run this setup code now. It is done. For the train and test final auto-tuned dataset. Now it is ready. Done. So now let's have a look with an image to an image example and corresponding mask, how it will be looking like. So that's why this display function is to be run with a mask. Already it has been run earlier, so it is appearing. Again I am running. Yeah, that we can see this cat very nicely. The masking is being done over there, right hand side. Now we are going to define the UNET architecture, the model. We are setting output channel equals 3. Now the base model I'm running. There are block 1, 3, 6, 13 and 16 where the sizes kept to be 64 cross 64, 32 cross 32, and it's going down to 4 cross 4. It's done. We can see over there all the detail of all the layers. Input, the input size 128 cross 128, 3 channels we have already kept at the beginning. It is intact. Then zero padding, then convolution, 2D convolution, which is resulting in 64 cross 64 cross 32. Then the activation function, and again here another convolution operation. For the batch, it is happening batch wise, so it may redundantly appear in this list. Convolution and ReLU, again zero padding, again ReLU, then convolution, again set of convolution and ReLU. Hopefully it is visible to everyone. Because it is happening batch wise, so many a times this will appear. I'm scrolling down rapidly. Okay, so because of the vast number of pixel depth, it is saying some 1 million more, approx 2 million parameters, and some 2 millions non-trainable parameters. So getting rid of 50% of the pixels. Now the decoder part, let us run this again. It's done. Now the UNET model for the output channel. we are defining over there. Now we are going to train it. Again, it will reappear. Yeah. As you can see, at the beginning 128 cross 128, then going down 64, 32, 16, 8 and 4. Again, it is picking up size 8, then 16, 32, 64 and finally 128 cross 128. So mirroring to the input image is only possible if the size is same. Now the architecture over there. Sequential, sorry, functional, sequential, concatenate, sequential concatenate, sequential concatenate, sequential concatenate, and the transposed convolution, transposed convolution. Now the masking done. Now we'll be showing the prediction, and so the prediction once again I am running live. Yeah, so that we can see the predicted mask over the cat at the rightmost figure, the true mask that we have already seen at the beginning, and this one is the actual input image. So here some improvement we're going to implement. Taking a little more time. It's only, we can see over there 3 by 57. It's taking bit time. 4 until 5. We can also observe the performance over there, accuracy 47% so far. 48, the accuracy is improving over there. Yes, 49. So till convergence, the accuracy will be still uplifting its value, and let us see how much well it can do the task. So for 52, yes, it is increasing. Let's wait for a little while. Meanwhile, this is the, okay, we'll come to that. Let us see once if it is done. So for 58, not bad. Because when we talk about research articles, we have seen people mentioning 99%, 98%, 92%, 85%. We don't know practically how much achievable. Yes, of course, it is achievable. However, we are not that much, we are still skeptical about the performance of works, but we have to believe if it is published in a reputed journal or conference paper like CVPR. So for 26, 27, accuracy stands 62%. Okay, meanwhile, let me open the base paper over there. As we know, this UNET was introduced in the year 2015, just 9 years back. Almost 1 or 2 years back, this GAN kind of thing also was introduced, but that is for different purpose. This is for different purpose. Many deep learning model between 2011 to 2017 have been introduced to the world of researchers, like GRU, GAN, and all. LSTM little earlier. So this research article, UNET, convolutional networks for biomedical image segmentation. The same three authors from Germany. Smart score. Okay. So with this, they mentioned that they have also won the ISBI Self-Tracking Challenge 2015. And along with computational efficiency, with the fastest deep learning network, compared to CNN also, they have done it in a better way when it is run in a GPU platform. So they have done the full implementation based on Cafe, and that link also being provided here. This for some people this paper might not be downloadable, so that I'll be sharing with all. Just I'm scrolling down. So for the mathematical model they have already prepared over there, pixel level. Augmentation is necessary because it is necessary for teaching the network the desired invariance and robustness properties. This is necessary when less number of training data samples are available, image samples are available. And when we talk about this microscopical images, so this says that we primarily need shift and rotation invariance as well as robustness to deformations and gray value variations. Along with that, random elastic deformation of the training sample seems to be the key concept to train a segmentation network with very few annotated images. When we think about microscopical images, that means we talk about cell level of analysis at that point, and when very less number of image samples are available, that generally happens in medical domain because of lack of subjects, and it needs a lot of ethical agreements and licensing and all. So with those challenges, they have come up with a good accuracy level. Let us check. Yes, it is done now. Again, going for the second box, and we can see the training loss is converging down, still going down. That means there are chances the accuracy may further increase, still going on. There you can see the true mask and predicted mask, the similarity, still some disturbance persists over there. For this second input image, there's not that much big difference between the true mask and predicted mask. The third one as well. So when visualizing through human eye, we can say UNET is quite better when we'll perform normal CNN. We might not be able to classify with that accuracy. It will further improve at this epoch, first level of epochs. Accuracy went up to 70%, and now second phase it is more than 86%. That is a achievable performance. Is a efficient way it is getting trained, and it is predicting the objects in a input image. Yeah, so the EM segmentation challenge, they are talking about this UNET 0.000353 is the warping error, and the pixel error 0.06, somehow little less underperformed compared to the dive proposed by some other group of researchers. These are the some experimental snapshots they have provided. Cell tracking challenge. So the same can be correlated with blood cancer, leukemia identification, sickle cell segmentation and all. Here UNET performed well with 92%, and this is we are not sure, but the data prepared by Dr. Sanjay Kumar might be a person from India. I have no idea. Working at Bioengineering University of California. Yeah, it's still going 87%. Still some executions to be done. Okay. 7 more iterations. But this will go on up to 10 epochs at least. So it will be time taking. However, this is how we saw the workshop level of execution for UNET. Now UNET further customized UNET, researchers have proposed, and let me stop sharing this. With this, I'd like to conclude this because this topic is not that big. Thank you all the professors, participants. It will be my pleasure in future if I'll be a participant for your talk as well. And if any feedback, inputs, please let me know. Suresh sir. Yes, Swata ma'am, are you there?
Thank you, sir. So any questions you can post in chat box. Sir is available. You can post in chat box related to the session.
Yes, my email ID also I am typing in there, ma'am.
Okay, okay, sir.
So that I am inviting, not I am inviting, I am interested to join if anyone would like to include me in their research work, project works, please let me know. This is my email ID. I am posting in the chat. group.
Yes, sir. Yes, sir. We can see, sir. Yeah. So really, it's a great presentation, sir, related to the UNET architecture and in the medical image sector. It's very interesting topic, sir.
Thank you, Sweta ma'am.
And truly grateful to you, sir, for this gracing this occasion. And we'll look forward for many more presentations from you.
It's my
Yes, sir. Practical approach is very good, sir. It's interesting. You engaged a lot with that.
thank you, ma'am. I'd like to thank everyone over there and my senior professors, colleagues, everyone. Heartiest thanks for attending this. Thanks MRC for providing me this opportunity. Once again, thanks to Government of India, and a special thanks to Dr. Suresh Kurumala.
I think with this we can end this session, and I thank a lot for this opportunity to host for this session. Thank you, sir.